Hi, my name is Ledesma. I am an undergraduate student majoring in biochemistry, and today I'm going to present a research project under the mentorship of Fahad Danlani and Dr. Krishna Rahesher. This project is called the Synergistic Effect of Calcium-Copper Mixing in Ternary Oxide Photoanodes for Solar Water Splitting. Let's start with the abstract. In this project, we mix different compositions of copper and calcium vanadate photoanodes via solution combustion synthesis in order to enhance the photoelectrochemical response of the mixture between calcium metavanadate and copper atoms in the parent metavanadate. All the methods used suggest that our polycrystalline product was a composite mixture of copper B2O6 and calcium B2O6. There's also strong dependence on the composition, and all composites are N-type semiconductors. Now, why are we doing this? What is the purpose of this project? One of the major global challenges is the huge energy requirements affecting the climate change, where the non-renewable energy sector is the major contributor to greenhouse gases in the atmosphere. We are constructing a clean, safe, and sustainable energy system, an artificial photosynthesis where we are splitting water into hydrogen and oxygen with the help of sunlight, and using the hydrogen as an energy source. And instead of having all those gases contaminating the atmosphere, we have hydrogen that can be converted into water again. We are looking on finding those efficient materials with the desired band gap and long-term stability against photocorrosion, which is the big challenge for photoelectrochemical water splitting. This first picture right here, showing the electrochemical cell, illustrates the goal of this project, to create a photoanode that in contact with sunlight could be able to split water into its components, and as you can see, to have the conversion of hydrogen into water again. This hydrogen evolution reaction can be seen here in the cathode, and the oxygen evolution reaction here in the anode. This second image right here shows a closer detail of what is really happening. When we shine sunlight, an electron is excited to conduction band, thereby creating a hole in the valence band, which were then used for HCr and OER. The next images show crystalline structures of copper B2O6 and calcium B2O6. Copper metavanadate has a triclinic structure, while calcium metavanadate has a monoclinic structure. Now let's take a look at the synthesis. We show here in solution combustion synthesis that we did. We dissolve a stoichiometric amount of malic acid, ammonium vanadate, and copper nitrate in water. After mixing and sonication, we burn it to take the water, carbon dioxide, and nitrogen off the sample. Once we had our product, we crushed up with the solid by using a mortar and pestles. We annealed it to take off the extra carbon from the first cooking, and we finally crushed it one more time to get our crystalline pattern ready for analysis. Here in the results, first we have our XRD pattern of all the samples. We analyze the end members by comparing them with corresponding ICDD card, as well as calcium B2O6, copper B2O6 composites in ratios of 1:3, 1:1, and 3:1. We can see that the diffraction peak intensity here of calcium B2O6 phase decreases gradually as the amount of copper increases. We can say that since all the peaks can be well indexed by copper B2O6 and calcium B2O6 phases, we obtained a composite system, and also some solid solution system because of the shift of the major peaks right here, you can see, to lower higher angles, which suggests a partial cation substitution. Now we have the Raman spectra that also shows that our mixture products are a combination of the typical Raman spectra of the end members copper B2O6 and calcium B2O6. The next graph right here is a linear swept voltammetry under interrupted irradiation of the samples, where we can see that the photocurrent intensity of calcium B2O6 increases significantly as the amount of copper increases. On this side, we can see the top plot for direct and indirect band gap of our products compared to the initial reactants. The optical band gap changes with varying copper content. And here our last images are scanning electron microscopy images. We can see the difference in size from the calcium metavanadate moving along with the different compositions. And finally, the copper metavanadate, which has a very small size compared to the calcium metavanadate. In summary, copper B2O6 and calcium B2O6 composites were obtained for the first time via time and energy efficient solution combustion synthesis. The optical band gap shifts to lower energy as copper content increases, and the PEC activity shows an increase in photocurrent density as the amount of copper increases. Thank you so much for your time and attention, and I hope you enjoy this project as much as we did.